Joel for introducing everything I needed for my talk. After he said he was going to focus on the combinatorial, I thought if I could switch up my talk a little and only do the topological, and that would leave Donald into a very different talk, I think, than he's prepared, so that doesn't work. But it would have been amusing if I could have left him all of the ergodic. Okay, so I'm continuing the discussion of the joint work with Donald, Joel, and Florian, and I'm going to focus entirely on the case of I also will not live up to the standard that Joel of clarity and how he wrote on the board, but I'll try. So stop me if I write too small. Of starting with a set of integers with positive density, and you can think of whichever type, upper Banach. I'm going to focus entirely on the case of two sets inside A. So this is the case that was done in their paper earlier, the paper from 2019 that Joel mentioned. And but I'm going to be talking about the proof that we use, where it will be, I hope, very clear what the generalization to K is. And so you'll see it in this. Okay, and properly, it should really say that there is a Fulner sequence along which you have positive density. I will say those things, but I won't write them on the board just in the interest of time. So the first thing is to give a new phrasing of, in terms of the combinatorics, of what's going on that will be more amenable to translating it into the dynamics. So what's the new phrasing is I want to say that A contains, and I'll write this as a shorthand, where you interpret this as A has positive upper density and it contains an infinite subset, B1 plus B2, if and only if you can do the following, which will make it very clear where I need to reverse limits. And so that's the advantage of how I'm going to write it like this. If and only if there exist infinite sequences, C1, C2 of integers, such that when, and so these are the enumerations of the sets, they're corresponding to the sets B1 and B2, if and only if, when I look at the indicator function of the set A, and I evaluate it along the sequences, C1 and C2, that either if I take the limit as m goes to infinity, and then the limit as n goes to infinity, or if I do the exact same thing with the reversing of the limits. So the limit as n goes to infinity and the limit as m goes to infinity. So this is reversing the order in which I have n and m of the same thing. So this is a combinatorially equivalent way to write this. And let me say more, because not just that these two limits are equal, but to actually be inside the set, these two limits should be equal to 1. Okay, so meaning that the indicator, that the sequences lie in there. So one direction of this, let me put this up, hopefully you can read it. And the point here is to really stress that this is allowing me to interchange the n and m, the order. I mean, that's the important part of this. So the first direction, the proof of this equivalence, this is obvious because you just enumerate the sets B1 and B2, and that produces the sequences C1 and C2. And the converse is also easy, elementary rephrasing of this, where you have to be very careful to apply the two assumptions. They're hidden here, really two different ways of viewing it. One is the limit as n goes to infinity of the limit as m goes to infinity, and the other is the limit as m goes to infinity of the limit as n goes to infinity, and they're both equal to 1. So what do I mean by that is you inductively pick the elements B1 of 1, meaning the first one that is going to go in the set B1, such that you get the right limit. So you take this one in the sequence B1, such that, well, to do this one, I guess it must be, well, I'm not sure which one it'll be, but it'll be the limit of how I've written it as limit as m goes to infinity, 1a B1 of m, B1 of C1, B2 m. Okay, so you first make a choice of B1, And then now you pick the first B2. So I pick the first element in the sequence B2 from the sequence B2 of M. And now what do I need to do? Well, first it has to satisfy the first thing. So that will mean that it has the indicator function 1a B1 of 1 plus B2 of 1 will be equal to 1. And then you apply the other limit to get the other one. So meaning then I will take the limit as n goes to infinity of the indicator function of 1. And now I will let this be 1 of n plus B2 of n, B2 1 rather, equals 1. And now I'm going to inductively go back and pick the first element B1, 2 in the sequence. So this will be in the sequence C1. And what you will do is, first of all, make sure that it satisfies this. Okay, you get that one for free. And then you will check that you get the limits. So you will take the limit now doing this way as m goes to infinity. So B21 of C2m will be equal to 1. And you alternate picking B1n and then B2n each time. And then alternately apply the limit assumptions to produce the sequences B1n and B2m. Okay, so first you pick the next one in B1 and the next one in B2. And this will allow me to get these limits. Okay, so I won't write any more of that, but it's just continuing inductively. So what this does is this formulation is what it allows us to, it's the same combinatorial statement. Okay, it's the same formulation that we have, but it makes it really explicit where we're going to do an interchanging of limits that's going to happen. This is the interchanging of limits that happens in the use of the tools that Joelle mentioned for the case k equals 2, namely Vitali's intersectivity lemma, is it allows you to do this interchanging of limits. But that one's a very particular to 2, whereas this one is going to make it clear the interchanging that will become more general for longer sequences and higher iterations. By the way, I'm focusing on this B1, B2, but if you want, I can point out where it comes up, where it's different for the other theorem that Joelle mentioned, which is B plus a translate T with the same set. But I think it'll make it clearer this way to make it what the different sets are doing. Okay. Now, it turns out that this formulation here is actually a little bit, in this exact phrasing, a little bit weaker than what we actually end up proving for higher k. This is for k equals 2, but for the higher k, this is somewhat weaker than what we proved. But what we actually end up proving is a statement that allows us to not just to interchange these two limits, but to allow a translate here on both sides by some other k. And this will kind of appear more generally when I get this into a dynamical statement, but that statement is one that we do not know how to prove for k bigger than 2 without proving this slightly stronger statement. And perhaps there is another way to avoid it, but we don't have it. Okay, so I think I can erase this because that doesn't give us much, and I'll use this board. Okay, so in order to turn this into a dynamical problem, we proceed exactly as if you were doing Furstenberg's proof of Semiretti's theorem, at least in the beginning. And we start by translating it into a dynamical problem using correspondence. Okay, so we have the set A, which is positive upper density, and you associate to it the system by taking the indicator function of this. So meaning you associate to it the point A in the sequence in 0, 1 to the end by putting in A and making it a 1 if and only if A of n is equal to 1, if and only if n is in A. You take this infinite sequence, take its, put the shift on it, the left shift, take the orbit closure of the left shift. So I'll write T I'm probably going to be lazy. I'm going to make it invertible, but this will be the shift. And take the orbit closure, e to the NA. Okay, so this is, I'm going through this quickly because I'm assuming that everybody here has seen this before. And so this is going to be the system, will be the system X associated with the shift on it. Okay. So A being non-empty, just the fact that it's going to have density, but in particular, when A is not empty, that tells me that if you look at the times that you're returning to 0, meaning the set of X's in the system. So E, I define this to be the set of X, such that X0 is equal to 1, then this set E, as soon as A is not empty, then the set E is going to be an open set. And when A has density, in fact, it's a clopin set in X. And when A has density, there's a T invariant probability measure on it. As I said, I wish I could have left all the measures for Donald, but so when A has density, it tells me there exists a T invariant Borel probability measure mu on X such that this set E has positive measure. Okay, so this is the standard setup of Furstenberg correspondence. And so what does this translation tell me is that now if I'm looking at the set A, which as here in this statement, A contains B1 plus B2 with B1 and B2 infinite, if and only if there exist sequences such that when I look at the indicator function of this, the set, which is corresponding to this point A in the system, and you take these iterated limits, you land inside E. Okay, that's what's telling me that the indicator function is. So let me summarize the equivalent dynamical. Okay, so what I mean by equivalent dynamical formulation is that this is equivalent to A containing B1 plus B2. But what I will just, instead of rewriting all of that in terms of the system, this is what I need to show. Maybe it's not I'll just put dynamical formulation, is assume that we have an ergodic system. And in the Furstenberg correspondence, I can pass to an ergodic system instead of by using ergodic decomposition. So I'm making a stronger assumption here. And E is going to be, well, it's clopin with positive measure. Okay, so that is the exact setting of what comes out of the Furstenberg correspondence. Then I want to say that if I started off with a transitive point, okay, the system that we obtained was the orbit closure of this point little a. So this is the transitive point we're showing. Then I want to show there exists, I'll write them as strictly increasing sequences of integers. Well, such that what happens when you go along the limit as n goes to infinity, or the limit as n goes to infinity, limit as m goes to infinity of the limit as n goes to infinity, you're iterating C1 of n, C2 of m, a. This should land inside the set E. And the same thing if I do the limit in the other direction. Okay, so limit as n goes to infinity, m. So one could rephrase this as A contains B1 plus B2 if and only if for an ergodic system, X mu T, and so on. Would be the equivalent formulation. Okay. Now, in fact, what we prove is something stronger than this, not just that you land both of these limits inside the set E, but that they land both inside the set E and you get the same thing. So I'm going to erase, just rewrite this as these two limits, a slightly stronger statement, are both equal to each other and inside the set E. Okay. So that's what we have to prove. Now, if this point A lies in the support of the measure, then everything becomes quite easy. Because if, but there's no reason a priori, just to warn you, that the point A lies inside the support of the measure. But if it does, then you would get that the set E would contain a shift of an IP set, the return times. And so since Joel defined IP sets, I can say this without worrying about it. Okay. And so, and you would get a much stronger conclusion, but as he pointed out, not every set of integers with positive upper density contains a shift of an IP set. Okay, so that's not a good method to try to prove this. Okay, and the problem is that A might not lie on the support of the measure. Okay, any questions of this formulation? Because now I'm just going to work entirely with this formulation. So it turns out we're going to move from this is the statement that we approve if it's transitive, but it's going to become a generic point. Well, so this is a topological dynamical system at the base, right? Because it comes out from first order correspondence as being a shift system. But for some, we cannot a priori assume that it's an equicontinuous system. But okay, you'll see exactly, it is somehow related, but you'll see exactly how in 1 second. Yes, this interchanging of limits is the important part. Yes, but okay, so the interchanging of limits, how do we study the interchanging of the limits? And so we need to keep track of the points that come in between that are sort of hidden in this formulation as I've written it here. And so since the cubes were introduced and the cubic notation has been introduced, what I'm going to use is the cubic notation for, I'll just do this with the two cubes. And that's where I said, you will be able to see very clearly what extends for K terms, because it will, every 2 cube will become a K cube. Okay, so the first point that we start off with is the point x00 in the base of the cube will be the point A that comes out of correspondence. Okay, the specific point, you have no control over that point, and that's an important thing to note, and Donald will have to deal with that in his talk. Okay, and then you take the limit of t to the point A, but I will look at it as, well, A. And this is, you look where the sequence goes along the point, and I can never do this without drawing a picture, so I will just draw the picture before I make errors. So if I start off here, this is a cube, and in this direction, I will be acting by the sequence C1, and in this direction, I'll be acting by the sequence C2. Okay, so what happens when you do x00 and I iterate, let's see, I wrote it with C1, I should end up with the point x01. And so the limit as n goes to infinity, and then x10 will be the limit, I'll write it as m goes to infinity, t to the C2m of the point A. So that means I've written it backwards from what I said, huh? Yeah. I have. This one will become a 1, and this one will be 2. Okay. And then x11 can be achieved in 2 different ways, right? So x11 should be the limit as m goes to infinity of the limit as n goes to infinity of t to the c1n plus c2m, which I'm now reversing which one's in them again. And it should be the same when I reverse the limits. Okay. So these are hopefully somewhat familiar by now of objects, but what we're looking at here is you take the point, this is x0, 0, you take the pair x0, 0, x1, 0, and you move by the power t cross t evaluated at c2 to the n, and you obtain 0, 1, 1, 1. And if you move from left to right, you take x0, 0, x0, 1, and you iterate t cross t along c1, you should end up with the right-hand side. So x1, 0 and x1, 1. So the cubes make a shorthand way of capturing all of the notation, all of the transformations that are going on here. But the important extra thing that's going on here is that the bottom is approximating the top along a sequence, and the left is approximating the right along the other sequence. Okay, so there's extra symmetries in here. And so what do we now have to prove is in order to get the dynamical formulation, to prove the dynamical formulation that's on the right-hand side, I need to show that there exist points that satisfy this. Okay, so again, we've gone through Furstenberg correspondence, and so we fixed a set A. It has positive density. So and by Furstenberg correspondence, we produced the system XT, the topological dynamical system. We produced the point A like this in the system. We produced the Clopin set E exactly before, and E, hopefully it's still there on the board. E is exactly the set of X such that X 0 is equal to 1, which is the same as T to the NA is in E, right? So A is equal to the return times of the set E. And then there is an ergodic T invariant Borel probability measure on this. And this point A that we started with is generic for this measure. Okay, so what do I mean by that? So, so again, the whole setup X mu T as before, and E, A, and A, all of the data that came from the right-hand side. And the point A is generic for mu, which means that it has good averages. If you take any continuous function and you look at the average of f to the Tn of x over in the right way, you approach the integral of f. Well, the point A, sorry. So A is generic for the measure mu. If you want, just continue thinking it's a transitive point. That will not be harmful. So what is the main goal? What we've done is we've translated the problem now to a purely ergodic statement that needs to be proven, is that this is an ergodic system. You have a generic point, so generic with respect to the measure mu that was produced this way. Okay, so that, and you have a Clopin set E, again, all of the same data. So mu of the Clopin is positive. And now what I need to do is I need to produce points, find a cube, x0, 0, x0, 1, x1, 0, x1, 1, which satisfies that picture, okay? So this is, we call this an Erdős cube. Let me just write that in this definition. So for tuple, and I'll go back to finishing the statement in a minute, x0, 0 satisfying this, okay? And by this, I mean these four equations. So these symmetries, you can think of it satisfying this picture, is called an Erdos cube. So our main goal is to show that there exists a quadruple, a four tuple, which satisfies the Erdos cube symmetries. The left approximates the right, the bottom approximates the top, and such that you have x0, 0 is equal to the point that we started with. You have to have it start at the right place, the point A that was produced from correspondence, and it ends inside the Clopin set. Yeah. No, so A is generic, comes out of the Furstenberg correspondence. It will be generic for the measure with respect to some Foldner sequence, but I'm kind of hiding all of the exact statement. Yeah, but there's some, so that comes out. And so what you now have to prove is that given an arbitrary generic point, in fact, the only one we really care about is the one that came out of correspondence. But the statement that we will prove is that when you have an ergodic system, a generic point with respect to that measure, and a set E with positive measure, a Clopin E with positive measure, that you can find a cube that starts at the generic point that was given and ends inside the open set that was given. Okay, and once we have this, now you can go back through the equivalent dynamical formulation, which I've erased, and you see exactly that this produces the sets B1 and B2. Okay. Any other questions, right? So this is the main goal now, is to produce these points. Correct. And we can't do without either one. That is also completely correct. We need it both topological and ergodic. And we will use very strongly the fact that this is hybrid in the sense that you just said. We need both the topological structure and the measurable structure. Okay. So the first question you might ask is, the key, let me just, before I say that, is the key thing is to produce this Erdos cube. Okay, it has extra properties, specific first coordinate, specific last coordinate. Okay, so first question you might ask is, why are there any Erdos cubes? Okay, these are four tuples in, you can think of them as points in x to the 4 that we would like to find. And so you need to know that, first of all, that there exists such a four tuple, and then you need to do the prescription of the first and the last coordinate. Okay. The part as prescribing the first coordinate, that's the really hard part, because it's a given generic point. You cannot change the point afterwards. Okay, now, hopefully this is reminiscent, and the notation that I've used is reminiscent of cubes, the dynamical cubes that were defined yesterday, I think in various talks. And so these are the dynamical cubes. I guess I will just write them just to remind you. This was the notation perhaps given as QK of X. So these are the dynamical cubes, which look like the orbit closures of P to the N epsilon of some X, where N is in, if I'm writing this in the, it's a vector, and epsilon is, I'm using the cubic notations where epsilon is going to be a K cube. I think this was introduced, I unfortunately missed yesterday. So I will just write this in case I'm using something that's not clear, please stop me. X is something in X, I'm fixing a topological dynamical system, and N is in ZK. This will be the bar closure. Okay, so those are the dynamical cubes. Every Erdos cube, if you look at the collection of all E, the K cubes, these will be all the Erdos cubes, meaning any quadruple that satisfies that or quadruple or K tuple. You can see the analogous definition in 3 dimensions. You would have 3 conditions. the bottom approximating the top, the front, the back, the left, the right for the faces. Okay, so you can see that these are all Erdos cubes are dynamical cubes, but Erdos cubes are not closed. Okay, I cannot take an orbit closure. And you can pretty easily construct examples to see the difference. You could make a very explicit combinatorial example by looking at subsequent sequences of numbers, by taking an indicator function of something where for a long period, I make it, this will be maybe, I can put down ones for a long period from some sequence an to an plus n, where the ans are very quickly growing, and I look at the indicator function of that in another sequence where I make it one from some other sequence, bn to bn plus n, another closely growing sequence. And then I could take the orbit closure by building these things by taking parity reasons. For example, maybe I'm in the interest of time, I think I'll skip this example and give you a purely dynamical example. But you could do something like this of taking along these ones, the indicator function of the evens, along those, the indicator functions of mod 3, for example. And then when you sum them, you would get something that is not going to be the indicator function of 5z, for example, and it would create problems because 2z is never going to be in the orbit closure. Iterates of 2z will never lie in the orbit closure of 5z. But let me look at the different example, one that's maybe a lot more familiar on the 2 torus. XY maps to x plus alpha, y plus x. Okay, this is a nice system that has appeared in several different guises. Assuming alpha is irrational, so this is a nice ergodic system. And if you can write down a cube, cubes are easy to write down here. So if we have x1, y1, xi, yi, I going from 1 to 4, this is a dynamical cube, only depends on the first coordinate. It only depends on what the y's are, meaning, so this will be these 4 points, x1, y1, x2, y2, x3, and so on. y1, x4, y4. This quadruple will be a dynamical cube, Q2, when x1 plus x4 is equal to x2 plus x3. And you don't really care what the y's do in order to get the dynamical cube. But to get an Erdos cube, it matters what the y's do. As you can, for example, see by taking all the points to be 0, 0, 0, 0, 0, 0. And now if you do 0, anything you want, it'll be a dynamical cube. But if I do 0, a half, this will not be an Erdos cube. Not. Because it matters, if you look in the picture, it matters that you get the right limits for all of the coordinates. Okay, because the Erdos cubes really depend on both coordinates. Yeah. Now, in a distal system, if you take the orbit closure of the Erdos cubes, you do get the dynamical cubes. So the first claim that I would like to address is that there actually are Erdos cubes. And in fact, there are many Erdos cubes, but you have to correctly interpret what does many mean. So the claim is there are many cubes, Erdos cubes. So let's look at the simplest case, which is not the 2-dimensional cube, but the 1-dimensional cube. Okay, so what's a 1-dimensional cube? It's kind of a trivial object, right? You're looking at pairs x0, x1 in x cross x, such that when you iterate the first one, you end up at the second one. Okay, so the limit of t to some sequence limit as n goes to infinity, t to the c1 of n of x0 should be equal to x1. Okay, I've written this down in the simplest case of the 1 cube. If A is transitive, right, A is equal to x0. If A is transitive, then obviously I get every x1. And so everything would be an Erdos cube, right, for any choice. So if A is transitive, then AX1 is an Erdos 1 cube for all X1. Okay. But not almost every point is transitive. Mu almost every point is not necessarily transitive, even if I started off with A itself being transitive. Even when mu is ergodic, it doesn't mean that almost every point is transitive. Okay, but mu almost every point approximates something that is in the support of the measure. And so using that, we can get that almost all the points are 1 cubes. Okay, almost all tuples. Okay, so what is that? The Birkhoff ergodic theorem tells me that almost every x in X is generic. Okay, meaning it has the right integral, the averages of all the functions. And so because of this little fact, which you can check, that if you have a generic point with respect to some polar sequence, or any generic point, just think of the regular averaging. And if a point Y lies in the support, then X can approximate that one. So what that tells me is that mu cross mu, and so mu cross mu, almost every X0, X1 is an Erdos 1 cube. Okay. Now, what happens when I try to do this at the next stage for the 2 cubes? I want to use a similar argument to say that almost all quadruples are going to be Erdos 2 cubes. The problem here is that I used the fact to say that almost every point is generic. The first fact that I used there, uses the fact that T is ergodic, because I'm using the ergodic theorem. And so for that, I would need that T cross T is ergodic to apply this argument, so that I can now continue in the same way that we did for the 1 cubes to see that almost all of them. And of course, it's not necessarily true that T cross T is ergodic. So I cannot repeat this argument. And so instead, the issue is what's the right measure in order to be able to say that almost every point quadruple is an Erdos cube. Okay, and so I think you have a good hint what the right measure is. It's going to be the 2 cubic measure in order to do this. So I guess I'll write the proposition. So the statement is that if you start off with, we're starting with an ergodic system, but keep in mind that X mu T is ergodic, then, and I think Donald will talk more about the measures, and so I will not say too much about this, but then mu2, it's just the 2 cubic measure, so it's the harm measure on the 2-dimensional cubes. Then mu2, almost every quadruple x00 up to x11 and x to the 4 is an Erdos cube. Okay, so this completely ignores, this says, with respect to this measure, almost all quadruples, with the analogous statement for k-tuples and higher dimensions, are Erdos cubes, but it completely ignores the fact that this is not proving what we needed to prove, which is that we have to not have almost everyone, but we need to specify the first coordinate. That's still a 4. That's a 4. Yes, it's a secret symbol used for, yeah. Yeah, I should write it, I get to be consistent. I should write it as x2. All right, so what I've ignored here is the fact that, we have to do a lot more than just say that almost every, but we have to specify it. Okay, let me just use the last 2 minutes to say, what do we need to do differently than producing the erdos cubes if we were looking at the other result? So this was the other result that Joel mentioned, which is B plus a translate. And here you do the same thing. You start off, you go through correspondence, you produce the measure, the ergodic system, x mu t, in the exact same way. You have the point A, which is still generic in the exact same way that we had for the other one. And we have to show now that there exist, I'll just write it as 2 points, x1 and x2, such that with that point A, they form a nice progression. So there have to exist x1 and x2 and some, this is in the space, and some integer t, such that what happens? Well, it's again the same thing of the first half approximating the second half, but what is the first half and the second half now changes. So this will be that the point x1 will be inside the set E. This is the same notation that I used before. So E is the clopin that came out from the correspondence. When you apply the transformation along the time t, t to the t is maybe not great notation, but this will land us inside the set E. And now you need the approximation part, which says that the first half approximates the second half, and that tells me that the AX1 will go to X1, X2 when I iterate this along the correct sequence, and this is exactly the sequence that's produced in the set B. So I'll write this as T cross T to the Ni, and this is as I goes to infinity. And you can think of this as a first half approximating a second half, but you have to be careful because they now interact with each other, the first half and the second. Okay, so this would be the corresponding statement, and then you would need an equivalent statement of almost all triples, and then you'd again have to worry about the point A being fixed in advance. Okay, and so that's what I'll leave for Donald to talk about. Thanks. No. So a priori, it's not ergodic, but by passing to a component, an ergodic component, it's basically the way Furstenberg writes it in his book. You can extract that from there. Well, so no. I mean, that's the whole point here, is that the point A, we don't have any control over. So that's why we prove that for any generic point, we're going to get this kind of result. And that's what we have to work hard on. Because a transitive point might not be in the support of the measure. So if that transitive point were in the support of the measure mu that is produced, right? So the point A comes out of correspondence and the measure comes out of correspondence, but there's no reason a priori that A lies in the support of the measure mu. So if it did, I could just do the whole proof with transitive and not worry about it. But it doesn't necessarily, and so I'm going to have to prove it for generic points. If we could prove it, it would be great, but purely for transitive. But to the real statement we prove is for a generic point. Okay, so Joel, Donald, and Florian proved their results in a more general setting for amenable groups. This does not go through for amenable groups for higher cubes, at least not as done, because we use the measures mu k, and as soon as you're beyond 2, mu 2, they don't know how to characterize them in the same way. I don't know. I don't know how it interacts with it. Because the point we produce is not going to be A. Just to iterate what? You mean to get topologic? So those will give us the dynamical cubes, but not every dynamical cube is going to be ergodic. We need more symmetries than that would give. So it might work as a different way to do it, but a priori, you're going to get too many and they won't necessarily be ergodic cubes. No,
Yes.
yeah, you can produce examples.
But the problem is the transitive point could not be generic point. It's
It's not generic, right? That's what I meant to say.
Yeah,
You're right.
yes.
So you're right.
Yeah.
That's not what I said, but not every transitive point
is
is a generic point. That's the problem.
Everything
We need a generic.
Yeah,
You're
so
right.
that's the
Said
point.
it right. Yeah, thank you. Yeah. Okay. Ready?